Okay, finally, let's, this whole time we've been talking about proton NMR, looking at the hydrogens in our molecules, but that is not the only nucleus that can be observed by NMR. Another very commonly observed nucleus is the carbon nucleus. Now, the only isotope of carbon that is visible in the NMR that can do that flip of the nuclear spin is C-13. That isotope. So it reads 13C NMR, but we read it as C-13 NMR is how we say it. Okay, here's a typical C-13 NMR, or one we might see. As we saw with proton, what does it have in common with proton? Well, we still get one signal for each unique carbon. So again, if there's symmetry, that makes one carbon chemically equivalent to another. They will coincide on the spectrum. Okay, our chemical shifts are a little different numbers. The protons were kind of 0 to 10. Here we have about 0 to 200, or maybe a little higher, so just a much wider range of chemical shifts. Okay, the signals in most C-13 NMR you'll see are typically all singlets. That's described as a proton decoupled spectrum. That's the most common experiment that we have. So we just see a line representing each unique type of carbon. Okay, but it is possible to determine how many hydrogens are on each carbon by doing a different experiment called a depth experiment. And using a depth analysis, you can learn for each signal, is that a CH3, CH2, CH, or just a carbon with no hydrogens on it. So it is possible to get that information, and very often that information is provided to you either by just telling you straight out, or by providing the depth spectra and having you interpret the depth spectras and just knowing the rules for that. But I'm not going to get into that here. Okay. One last thing to note, though, is since all we can see is the C-13 isotope, that only accounts for about 1% of the carbons in any structure. And so you either have to have more sample if you want to acquire a C-13 NMR, you have to have a larger size sample, or maybe just spend a longer time acquiring more scans on the spectrum. So a lot of times it takes longer in order to bring down the noise of the signal and get a good C-13 NMR. So let's take a look at what affects the chemical shifts of C-13. It has the same concept as proton NMR in that if you are electron rich and shielded, those are things that come upfield and closer to zero. Where down here we have electron deficient carbons that are deshielded. Okay, so that concept still holds. What we find on the far right then are our plain old alkane carbons. And if we attach a halogen or a nitrogen or an oxygen or something electronegative, we would expect that to cause a downfield shift. Remember our little triangle for the upfield versus downfield. So going to the left would be a downfield shift. Triple bond, comes more around 80 or so in that range. Carbon-carbon double bonds, either for alkenes or for aromatic, for benzene rings, those kind of come in this range, 100 to 150, something like that. And then at the very far left, what we have on the most deshielded are the carbonyls. So carbonyls are very easy to pick out in a C-13 NMR. They're somewhere around 200. Carboxylic acid derivatives are a little more shielded because these groups all add electron density by resonance. So these are more electron-rich carbonyls. That brings them a little to the right, a little upfield, where aldehydes and ketones are going to be a little higher than 200. Okay, so to look at some numbers, again, you'll typically be provided with tables for these. We see a slight difference depending on whether it's a primary, secondary, tertiary, or quaternary alkyl group. So the primary alkyl groups are the most shielded, just like the methyl is the most shielded. And for proton NMR, same is true for C-13. So those are the ones that are furthest to the right, furthest upfield. They move down a little bit as we add carbon groups on it. Attached to iodine, bromine, nitrogen, chlorine, oxygen, depending on what heteroatom we have slightly different ranges. Okay, but as you might imagine, those shift them all downfield a bit. Okay, then we have alkynyl is a little further downfield still. Alkene and benzene, not so easy to distinguish here. because they all kind of come a very similar range, 100, 150, somewhere around there. And then, like I said, the carbonyls, depending on whether you're a carboxylic acid derivative, with a group on here that will add electron density. This is more electron rich, and that shields it and brings it to a lower number. And aldehydes and ketones bring it to just, usually a little above 200, at or above 200. Okay, and we'll just work through a couple of problems. Typically, C-13s are provided in conjunction with the proton NMR, and we saw how many proton NMRs we solved without even needing a C-13. So C-13 just to kind of add some additional information, but it really should just confirm what you've already found using the IR and the NMR data, the proton NMR data. But it is possible using the same strategies we had before to solve a C-13 NMR. But there's a lot less information in here, so it's a little harder to put the molecules together if you're given only a C-13. But let's try it in a couple cases. This first one, we'll start as usual. We'll work with the formula since it's given to us, C6H14. If this was saturated and we had 6 carbons, how many hydrogens could we expect? 2n plus 2 is 12, plus 2, it would be C6H14, and we have C6H14. So that tells us it's saturated. That means there's no pi bonds, there's no rings, right? That's what that lack of degrees of unsaturation tells us. Okay, and what we see here is I've drawn on top of each peak what how many hydrogens are attached to each. So this has already taken that depth information and incorporated it into the C13 spectrum. And so this kind of tells us our pieces. We have a CH. We have 2 CH2s. Okay, notice I'm always drawing them with the appropriate arms so I know what they can be attached to. We have 3 CH2s. We have a CH3. We have 2 oxygens. Okay, and then we add up. Do we have our pieces? We have 1, 2, 3, 4, 5 carbons. We have C5. We have 3, 4, 5, 6, 7, 8, 9, 10, H10, O2. So actually, these pieces have not accounted for all of our formula. We're missing a carbon, and we're missing 4 hydrogens. So how can we make this work? Well, one thing we can do is we can have a CH3, another CH3. So you see how this peak is a little bigger? Sometimes that can give us a clue. Sometimes the size of the peak is proportional to how many hydrogens are on there. You see a little difference there. A quaternary carbon is usually a pretty small peak. But in these generated spectra, this is a bigger peak because there's more than one methyl group that's contributing to it. So just like the magnitude of the area under the peak is proportional in the proton NMR, the same is true for the C13 NMR, but we're not given integrations in this case. So you wouldn't know for sure, other than maybe seeing a difference in the size, exactly how many methyl groups there are. So what we could do is we could say we have 2 CH3s, and then we only have 1 extra hydrogen that we need to account for. We have 1 extra hydrogen. Now we have C5H10O2 adding up. Now where can we attach that hydrogen? We can't put it on any of these carbons because we've already indicated how many hydrogens are on each. So what we could do is we can combine this into an OH group. That hydrogen must be on an oxygen, and that's why it wasn't showing up in our C13 with our depth analysis. Okay, so let's start putting them together. We have some oxygens to play around with. Who do you think is attached to an oxygen? Which of these pieces does it look like are attached to an oxygen? Looks like we have a CH and a CH2 and a CH2 that are all pretty far downfield. Okay, so I think these all have oxygens attached. And we have these CH3s. We have 2 CH3s that are equivalent. how can we have two CH3s that are equivalent to each other? Well, we can put them on the same carbon, and which piece can they attach to? They can't attach to a CH2 because those would be putting two N pieces on onto a CH2. So really the only way we can attach these two CH3s is by using the CH that's given. So this CH, we put two methyl groups on it, and then that accounts for the fact that both of these are chemically equivalent and they show up as just one signal. Okay, now what did we say about that CH? What do we think that CH is attached to? I think it's attached to one of the oxygens. So that will take care of one of our oxygens. I can't put an OH here because, again, that stops the molecule. I have to put on a piece that has more arms. So what can come next here? How many choices do I have? There's only one choice. I can only put a CH2, and then the other CH2, and then the other CH2, and then finally the OH. There's only one way to put these pieces together. So the trickiest part here is to, that also accounts for the chemical shift. We can't use coupling, we can't use those splitting patterns anymore to decide who is attached to whom. We can only use chemical shifts when we have a significant function group that alters that. So really a C-13 is very difficult to put a molecule together, except in certain circumstances like this we can do a pretty good job there. So before we leave though, let's just double check if you had to predict what the C-13 NMR would look like for this. What would we have? Well, we would have, we can go ahead and label these A, B, C, D, E, and make sure we can identify them and bring them together. We should have two methyl groups that are chemically equivalent that come as one peak and that are just attached to a regular carbon, so they should not be downfield any great amount. And so that makes sense with this. It's coming at 22 ppm. So these are, this is E. Here we have a CH signal that is attached to an oxygen, so that should be kind of a higher number. So that looks like A. And this is at 76 ppm. There's not much you can predict, a lot of specifics you can predict for your C-13 NMR, other than the number of signals and approximately where it might be. Okay, and then we have a CH2. We have three CH2s. Two of them are attached to oxygen and one is not. So which one, this middle one is the unique one, and who would that be? That would be this CH2, the one that's furthest upfield. And then the others, B and C, we can, one is attached to an OH, one is attached to an OR. So those are going to have different effects in their deshielding. There are tables to calculate your C-13 chemical shifts as well. So if you had access to a table, you can more precisely determine exactly which one is B and which one is C. But without having access to those tables, right now we wouldn't be able to distinguish between those two and decide exactly which is which. Okay, let's try one last C-13 problem. C5H8O2. If that were saturated, what would our formula be? C5H2N plus 2, 10, 12. C5H12 would be our saturative formula. We have C5H8. So we have 4 hydrogens missing. So we have 2 Du. Okay, what pieces do we have? We have a carbon with no hydrogens attached. We have a CH2. I'm sorry, we have 4 CH2s. Those are all the rest of our pieces. And then we have 2 oxygens. And we have 2 DUs. So there's a lot of missing things here. Now, the one thing I'll bring your attention to is this. This one carbon is very far downfield. So far, it's pretty close to 200. It's 172. So what kind of carbons show up that far downfield in the C-13? it must be a carbonyl. So I can take care of some of these pieces by having a carbonyl. And in fact, having it closer to 170 rather than closer to 200 probably means I have an ester, but we don't really have to. So in other words, I think that other oxygen might be attached here rather than having a ketone, but we don't really have to jump there quite yet. Okay, so where is our other DU? It could be a double bond or it could be a ring. Do we have evidence of either? If we had a carbon-carbon double bond, what would we see in the C-13 NMR? We would see peaks somewhere in here, 100 to 150. That's where our alkene or our aromatic carbons show up. There's nothing here. There are no other pi bonds besides this one carbonyl. So there's no carbon-carbon double bond. So what does this DU have to be? It has to be a ring. It has to be a ring. So how can we arrange these atoms? Do we have any evidence of a carbon attached to an oxygen? We do. We have this CH2 is the furthest downfield, so we have one CH2 that's attached to an oxygen. The other CH2s are not. So what structure do we come up with? The only way to put these guys together is by making a ring and have one end reach around and come up to the other end. Rings are pretty tricky in the NMR because a lot of times they're kind of building our structure. If you ever find yourself with two end pieces but you've run out of parts to put in, see if it's big enough to come together. 5-membered rings, 6-membered rings are very common in organic molecules, and so a lot of times that's going to solve a problem for you, and this is one of those cases. Okay, so we could double check. Do we have C5H8O2? We forgot to do that before we started putting them together. 1, 2, 3, 4, 5. Yes, we have 5 carbons. We have 2, 4, 6, 8 hydrogens, and we have our 2 oxygens, so our formula is correct. Our chemical shifts are good. We would expect this. And just like we thought, having it be an ester brings it more in the range of 170. And it's a carbon with no hydrogens on it, so this is a carbonyl, somewhere around 170. And then we have one CH2 that is alpha to an oxygen attached to an oxygen. So that's at about 70 ppm. And then all our other random CH2s are all ordinary alkyl CH2s coming in this range from 20 to 30. Okay, so do get some practice with C-13. You'll find some different exercises that you have to do with those. It's not so common to have to solve a C-13 with no other data. But if you're lucky enough to have a C-13 provided to you, along with an IR, along with a proton NMR, make sure you use all that information when you're coming up with your pieces. And most importantly, in all these NMR problems, once you have come up with a structure and you think you have that answer, stop, put the spectrum away, look at your structure with fresh eyes, and one by one predict what your spectra would look like, what your IR spectrum, your proton NMR, your C-13 NMR. Make sure that all the parts you have in your structure are accounted for in the spectrum. And then the good news is you know you have the right answer before you can wrap up and move on to the next problem.